Hello all, this is unit 3.7 and it's rational functions. So we're going to figure out how to do intercepts. We'll first figure out what they are, how to do all the intercepts, and then something called slant asymptotes of rational functions. So to get going, we first want to figure out what the definition of a rational function is. And it's any two polynomials written in a ratio. So what we mean by that is it could be a quadratic over a cubic, or just any combination of a polynomial function over another polynomial function. Goodness. Okay, so moving on, say we want to find the intercepts of this function. So if we think about it, for an x-intercept, that's where we want y to be 0 or the whole function to be 0. So if we need to figure out that, if we make the bottom 0, it's an undefined function. So the x-intercepts are where the top is 0, because 0 divided by any number except 0 is 0. So for the x-intercept, we set each factor in the numerator equal to 0. Okay. If it's not factored, you want to factor it out or use one of our other methods to figure it out. So we're going to do x minus 2 equals 0 and x plus 3 equals 0, which gives us the intercepts x equals 2 and x equals negative 3, which put in intercept form is 2, 0, negative 3, 0. So those are x-intercepts. Now to find the y-intercept, the y is where we plug in 0 for x. Sorry about that. I had to figure out how to clear the page. All right, so for the y-intercept, think about what that is. That's 0 comma something. So we set all x is equal to 0. Okay, so I'm going to do f of x equals 0 minus 2, 0 plus 3, 0 minus 1, 0 plus 2, 0 minus 5, or negative 2 times 3, negative 1, 2, negative 5, which reduced down gives us negative 3/5. So that makes our y-intercept 0, comma, negative 3/5. All right. So then with a rational function, let me erase this real quick. Yeah, just hit clear. There we go. With a rational function, because we're going to have possibility of zeros in those denominators, you know, if x is negative 1, if x was if x was 1, negative 2, etc., we have this idea of a vertical asymptote. So a vertical asymptote is where the denominator of the function is equal to 0 and the numerator is not 0. So I'm going to highlight that part too. If they're both 0, we have something called a hole. So what a hole is on a graph, it physically stops and keeps going with whatever it's doing, but there's a hole. So if we have 0 over 0, you get a hole. Otherwise, we're looking for where that denominator is equal to 0. Okay, so kind of make sure you write that down, get your definitions, pause me at any point. So this idea of a vertical asymptote in a hole. So at some point, if this denominator is 0, we can't have that. So we've got to figure out where it is, because that'll end up graphing as some type of hole, or it might end up being this way. But we have this idea of a vertical asymptote, which is where the graph cannot be. So for your vertical asymptote, what we do is we set the denominator equal to 0. okay? And then the non-canceling factors on top and bottom are your vertical canceling asymptotes. Again, it's non-canceling because if they cancel, we get a whole. So up top, we have x minus 2. And when we factor the bottom, it's x minus 2, x plus 2. That's that difference of squares factoring pattern. So these two at x equals 2 represent a whole. But this one at x equals negative 2 is a vertical asymptote, meaning the graph can get close to it but won't actually hit it. We cannot have a negative 2 in the denominator. Oh. So on that note, we also have this idea of horizontal asymptotes of a rational function, meaning when I'm drawing this, I can have this vertical one that I can't touch, but I could also have a horizontal one that I can get close to but not touch to and have some type of graph like that. So I find my vertical by setting that denominator equal to 0, and I find the horizontal by using the rules up here. So the rules that I'm showing are if the degree of the denominator, so when we're talking about this, the degree is the highest power on it. So if I have x3 over x4, the degree of the denominator, the bottom one, is greater than the degree of the numerator. That automatically says that y equals 0 is our horizontal asymptote. So that's case 1. Case 2 is now if the degree of the denominator is less than the degree of the numerator, denominator. So if the degree of the denominator is less than the degree of the numerator, there is no horizontal asymptote. That's case 2. And then case 3 says if the denominators are equal, if the degrees are equal, meaning, let's see, I'll have some quadratic up here and another quadratic down here. All I'm looking at are the degrees of the leading term, so those highest degrees. And then what I'm going to do with those is I'm going to do the ratio of their coefficients. Okay, so it would be the ratio of the leading coefficients if they're equal. So it would be 2 over 3, which means y equals 2/3 is now that horizontal asymptote line. So those are your 3 different cases for horizontal asymptotes. You may want to write them down, have a quick sheet to look at as you go through. So you can have the degree of the denominator being bigger, smaller, or equal, and you have your 3 different options. Okay. So looking at a couple examples, if I want to figure out the horizontal asymptote of the following rational function, what I'm going to be looking at is the top degree of the top and the leading one of the bottom. So I'm going to rewrite these in order. So I'm going to write m of x equals, on top I have no x squared term, then I have minus x plus 5. On the bottom, I have a 2x squared plus 7x plus 3. So if I think of it this way, 0 over 2 gives me 0, so y equals 0 is my horizontal asymptote. So if I rewrite it that way, if you're missing that term, think of it as a 0, and then it's a little less to memorize. So in this case, degree of denominator was 2. It was bigger than the degree of the numerator, which was 1. So we end up with y equals 0 being that horizontal asymptote. And then if I keep going for another example, I want the horizontal asymptote of the following rational function. So again, let's put that missing piece. So if I do 2x squared plus x minus 1 and put in that x squared that's missing, and I look at that, 2 over 0 is undefined, which means there's no horizontal asymptote. Okay. So if you look at it that way, it's a little more helpful. And if I keep going, if we want to compute all of the horizontal just the horizontal asymptote of the following rational function, just look at your leading terms. That's all we ever really need to look at with these anyway. Those are equal. So we are just going to do the ratio of the leading coefficients, which means y equals 2/3 is my horizontal asymptote. All right, and pause at any time and go back and take a look if you're not sure. Okay. And then for oblique asymptotes, so this is a little different. So in this case, we don't have an x squared term. Okay, so there's no horizontal. But if there's no horizontal, we could have another type. We could have one that's slanted or oblique, and it could be a straight line, it could be a parabola, but we could have other ones in here. So what happens if you find that there's no horizontal? You perform the division to get the oblique. So if the bottom one can go into the top one, meaning degree of the denominator is less than numerator, then we divide. This one lends itself nicely to synthetic division. So I can take the 0 out of here. X plus 1 is the factor, -1 is the 0. And I can take the coefficients off of my top numbers, bring it down, multiply, add. Multiply, add. Okay. So then that quotient right here is your oblique asymptote. So over here, it would be the line y equals -x plus 3 is my oblique one. So that means on my graph, -x plus 3 is the line it can't cross. Okay, so if it's not a horizontal, try dividing it in and you can get that slant or oblique asymptote. Okay. So this is what that one looked like with that slanted one. So here was our -x plus 3 one. And it's showing that the graph can go close to it, but not quite touch it. Okay. Now, if I keep going, okay, so then what we can do, if we have all of this information, is we can go backwards. If we have the graph, we can figure out what the equation was based on all of the intercepts and the asymptotes. So the horizontal intercepts and the vertical asymptotes tell us what all of the factors are on top and bottom. So the vertical asymptotes become all the factors in the denominator, and the horizontal intercepts become all the factors in the top. And then don't forget, we still have this A term that we have to test with a point. So looking at that, if I'm taking a look at this one, it has a vertical asymptote at x equals 0. And then it has just that one. And it has a single root because it has this form. So we are 1 over x. Doesn't have any others, so it doesn't have any of the factors on top. Whereas this one, oh, sorry. Sorry about that. Has a double root at the x equals 0 because of its behavior that's going on here. So single, double, so it's 1 over x squared. Now, if I go back up here, any of those horizontal intercepts are going to be that top portion, but these don't have any of those, so that's why the number on top is just a 1. And then we're looking at what type of behavior is happening at those vertical asymptotes, which are at x equals 0. Oh, sorry. So then the next one, we have quite a few things going on. So this would be a good one to pause and try it on your own real quick and see if it works for you. Okay, so taking a look at this one, we have a couple of different things going on. So we are looking for some f of x equals a, and then we have numerator over denominator. So if we go back up here, the numerator is going to be made of horizontal intercepts, and the denominator is going to be made of vertical asymptotes. So if we come back here and take a look at this, if we look for all of those zeros, you have one at 2, sorry, -2, and one at 3, and those are both single. So what those are going to become is our numerator. So we're going to start to build this. I have a, and then I'm going to have x plus 2, x minus 3. And then those vertical asymptotes are going to become our denominator ones. So if I come over here, I have one at -1 and one at 2, but then this one's a single because they're both going opposite directions, but this one is a double because both are approaching it. So 2 going towards it, that's a double. So in our denominator, we're going to have this x plus 1, we still go the opposite, and then this x minus 2, but it's going to be squared because we have a double root there. So what we have left to do is figure out what this a term is. So we figure out that by looking at any point on here that's very clear. It's the easiest is to probably take that y-intercept because we get to set x equal to 0 for that. So over here we have this y-intercept at 0, -2. So we're going to zero out all our x's. So we have f of x equals a, 2, -3, and then 1, -2 squared. So that leaves us with one of the 2's cancels. So we're left with, -6 over 4a, making a, I ran out of space here. Hold on a second. All right, let me come up here. So I've got this point 0, -2. So I'm going to do -2 equals a. And then I'm zeroing out all of my x's. So I have 2, -3, 1, -2 squared. All right, so what that leaves me with is -2 equals a, -6 over 4. And then that, with a little bit of algebra, gives me 4/3 as my a value. So then finally, I put all that together and I get f of x equals 4/3. And then we write all of those different factors we already found, x plus 2, x minus 3, x plus 1, x minus 2 squared. And then we are done.